So we've been talking about stoichiometry, and we talked about really basic stoichiometry problems. And I sort of consider basic stoichiometry problems, as I mentioned, sort of problems where you're really only given one piece of information about somebody in the reaction. Maybe you're given something about the reactants, maybe somebody about the products. And in those sort of steps, really the easiest way to kind of calculate what you need is to just follow the 4 steps that we've been talking about, which is make sure you have a balanced equation, you convert to moles, do the mole to mole relationship, and then at the end there, if you need to, convert those moles into some other unit. The reason we don't have to worry about limiting reagents and those type of problems is sort of assume that, you know, whatever they gave you is either, if it is a reactant, that's the limiting reagent. So that's why I didn't give you the other reagent. It's assumed to be in excess. And obviously, if you're given a product, that's just how much product you produce and stuff like that. So in problems where, like this one here, we're going to go through, where in this case, we have 124 grams of aluminum is reacted with 601 grams of iron 3 oxide. We want to know how much aluminum oxide we would produce. Those are both reactants, and we have grams of both of the reactants, which means we definitely could get to moles of both of the reactants. And that really is the key to know that this is a limiting reagent problem, and you do need to figure out, you know, which one's the limiting reagent as you go through here in order to calculate how much product you produce. Now, there's multiple ways that you could do these problems. A very common way is to just do 2 separate stoichiometry problems, one with each of the reactants, and figure out how much product each one produces. And, you know, the one that produces the least amount is the limiting reagent and how much you would yield. Another way is to do a little calculation to figure out, you know, if I want to use up one of the reactants, how much of the other one I need to put in there, and do I have enough? And those are good ways to do it. And again, if you have learned this maybe in the pre-class, how to do it that way, and you want to do it that way, is perfectly fine with me. I don't really care which way you kind of do it, as long as you pick a legitimate way of obviously doing it. The way I'm going to show you is a little bit different because it can be very helpful in a lot of problems, because in these problems, they do ask, you know, how much product you produce, and they sometimes ask how much of the excess reagents left over. So the way I'm going to show you will allow you to relatively quickly get to all those answers without it maybe having to go all the way back to the beginning and sort of start over with another separate calculation. So the way I'm going to show you will allow you to figure out, you know, how much of both products you can make really quickly, how much of the excess is left over, and those type of ways. So that is sort of the process I'm going to show you. And if you like it, you could use it, obviously. We'll show you maybe an example of the other way to do it as well. But again, you can use whichever way you're kind of comfortable doing it. So the first step, no matter really which way you choose to do these type of problems, is really the same couple of steps that we did with basic stoichiometry problems. We want to make sure, again, that we do have the equation and its balance, which obviously it is. We also want to convert whatever they gave us into moles. So that is what we'll do here to start with. We're going to convert both of what they gave us into moles. So we're going to take 124 grams of aluminum. We're going to use the molar mass from the periodic table. I think it's still 2698, I think. That's good. Getting old. 2698 grams per mole. We'll also do the same thing with our iron 3 oxide there. We got 601 grams of iron 3 oxide. Adding up the molar mass from the periodic table here. We have 2 irons at 5585 plus 3 oxygens at 16. Looks like it gets us something like 159.7 grams per mole of iron 3 oxide. Once again, really just the same starting steps that we did before. So 124 divided by 26.98 gets us something like 4.59, we'll call it 6 moles of aluminum, and 601 divided by 159.7 gets us 3.763 moles of our iron 3 oxide. So what I'm going to show you now is what is sometimes referred to as using ice tables. And we could use an ICE table to help us solve these. ICE here means initial, change, and in this case, it means end. Also, the benefit of doing this is if you do plan on taking 200B, you do ICE tables all day, every day. So it'll be helpful if you go off to 200B. And 200B, the E stands for equilibrium, but here it just stands for end when we're doing it here. So we're going to use this sort of table to help us figure out pretty much everything that we're looking for. So I'm just going to recopy here, I think, the equation on the next page. So we got 2 aluminum plus 3. Oops. All right, so that should be right. Okay. So we're going to do our ICE table. So we're going to take the equation and we're going to start with the initial. And the initial here is going to be the moles that we just figured out. So initially for our aluminum, we had 4.596. Iron 3 oxide 3763. And initially we could safely assume that we have none of our products. So nothing of our products is made. We have just our reactants at this point. So these are our initial moles of our reactants. Now, as this reaction takes place, it's going to go from the reactants to the products. That means that should the amount of reactants increase or decrease with time? The amount of reactants should decrease with time, right? Because you need to use both of those guys to make products, and the products would increase with time. So we represent that in the ICE table as minuses on the left-hand side, pluses on the right-hand side, and we use X to represent the change. So we use X to represent the change. Now, a really important part of the change part here is it is actually where we take into account the stoichiometry. So this would be minus 2x. The 2 here is for the stoichiometry, the coefficient. This would be minus x, as the coefficient here is 1. And we want to do that on the other side, which should be increasing. So this would be plus x, which once again is the coefficient, and plus 2x, which is a coefficient. If you do not put those 2's and the coefficients in there, you frankly did the wrong mole-to-mole relationship. So that is what those 2's are for, is the mole-to-mole relationship, the stoichiometry part of it. So really important in the change part that you put those numbers in, and they are just like what we do with stoichiometry. They're pretty much just the coefficients. So you want to include those in there. Any questions so far? So what we're going to do now is simply just bring everybody down to the end line here. And this would give me 4.596 minus 2x. I'm going to take the moles out for a second. 3.763 minus x, x, and 2x. Any questions so far? So I remember that we still need to figure out which one is the limiting reagent. And we're going to do that by basically setting each of those guys equal to 0 and solve for x. So we're just going to set each of those guys equal to 0 and solve for x. So this would give me 4.596 minus 2x is equal to 0. Basically gives me 2x is 4.596, which gives me an x of 2.298. And those would be moles. We're going to do the same thing to this guy, which is pretty straightforward. This is 3.763 minus x is equal to 0. That means x is equal to 3.763. Any questions on that? So set it equal to 0, solve for x. The x that is the smallest is your limiting reagent. So in this case, the x value that is the smallest here is this one. That means in this problem, the aluminum is our limiting reagent. By default, that would mean the iron 3 is our excess reagent. Right. Any questions on that? So here's where this part is pretty good. We're going to get rid of these numbers because we don't need it. Obviously, it's the too larger number. This X value that I just solved for, this X value is this X value in the table, is this X value, it's this X value, and it's this X value. So it's all those guys at the end. So we will solve for what was asked for first off, which was how much aluminum oxide. And we can see that the moles of aluminum oxide is equal to X. And we see that X is equal to 2.298 moles. And now we can use the molar mass of aluminum oxide to convert those moles into grams. So if we do that, aluminum is 2698. There's 2 of them, and there's 3 oxygens, which gives you about, we'll call it 101. Now we'll call it 102. 102 grams per mole. And if we times that by 2.298, gets us about 234 grams of aluminum oxide would be produced. That would be our theoretical yield in this case. That is the maximum yield that we should get. First off, any questions on any of that? Now, the benefit of this is what happens if I want to know how much iron I would produce. I could then go to my table and I could see really quickly that the moles of iron is equal to 2 times X, which would be 2 times 2.298 moles, which would tell me that I would have produced 4.596 moles of iron using the molar mass of iron from the periodic table, 5585 grams per mole, would tell me that in addition to my 234 grams of aluminum oxide, I would produce 257 grams of iron would also be produced. So you can see very quickly, you could figure out how much iron that you did. The other really nice thing about this is if I want to know how much of my excess reagent was left over, that would be this guy, right? That's my excess reagent. So I could figure out the moles of my excess reagent, which is iron 2 that's left over, is equal to 3.763 minus X, which means 3.763 minus 2.298 tells me that I have about 1.465 moles of iron 3 oxide left over. I'll go up on top since it's a little bit hard to see up here. So we'll go over here. Get rid of some of that there. There we go. So by putting it back into there, I had 1.465 moles of my iron 3 oxide left over, which obviously I can multiply by the molar mass that we had earlier for that, which was 159.7. And I would see that I had about 234 grams left over. So again, very quickly, you could answer pretty much any stoichiometry question that would be asked of you. You know, how much products you would produce, how much of the excess left over, how much of the excess reagent you would have left over. Very, very quickly without maybe having to start all the way at the beginning and kind of coming back and doing some separate calculations. So it kind of organizes everything for you pretty good. Obviously, if I put my X value into the aluminum, I pretty much should get 0, right? Because it's the limiting reagent, it should be left over. Nothing should be left over at that point of that. Any questions on any of those steps? So again, this is a convenient way to sort of answer all those questions very quickly. If you like it, you could use it. Again, Two other common ways is just to simply do two separate calculations from each reactant, figure out how much each one produces, and the one that produces the least amount would be the limiting reagent and your theoretical yield. The deal with that one is if you did want to figure out how much leftover reagent, you got to kind of go back to the beginning and do a separate calculation and stuff like that. So it's perfectly fine if you like to do it that way. Like I said, I don't have a preference of which way you do it, but you could try this way if you like it better. Any questions on that there? Okay, so why don't you try one here? Let's try actually I'll just make up one here real quick. Let's do we'll do the guy that we did before. We'll do this one here. So how many grams of NH3 would be produced by the reaction of, let's do 12.5 grams of H2 and 7.25 grams of N2. All right, so take a couple minutes, see what you come up with. Again, nitrogen 1401 and hydrogen here 1.008. Okay, let's take a look. So once again, we're going to start with identifying that it is a limiting reagent problem. We are given grams of the H2, we are given grams of the N2, and that obviously is enough to get the moles of each of those reactants. So again, somewhere along the way, we need to determine that. We'll start like normal. So we do have our balanced equation. We do need to convert into moles here. So we're going to take our 12.5 grams of H2. We're going to use the molar mass there for the periodic table, 2.016 grams per mole of H2. And that is going to get us looks like we'll call it 6.200 moles of H2. We're going to do the same thing here for our other reactant, 7.25 grams of N2. Going to use the periodic table there and do a 1401 times 2. Gets us a 28.02 grams per mole of N2. Once again, the grams would cancel, and that would give us 7.25 divided by 28.02. And that would give us something like 0.2587 moles of N2. That again is our starting amounts of each of those things. First off, any questions on that there? All right, so I'm gonna solve this using the ice table approach so you can see it again in case you like it. So we're going to do our equation. We're going to put in there initially our initial moles. So I believe the H2 was 6.2. So 6.2. And our N2, 0.2587. And once again, here we could safely assume that we are starting with nothing of our products. Once again, this reaction should be heading to the product side, which means our reactants should be decreasing, products should be increasing. We're going to represent the change in the moles as X, but we do want to make sure we take into account the coefficient. So that should be minus 3X minus X. Again, otherwise you will be wrong in terms of your stoichiometry, and this would be plus 2X here on the back end. Bringing everything down, and again, I'm just going to get rid of the moles so it's not too crowded here. 6.2 minus 3X, 0.2587 minus X, and 2X. First off, any questions on the table there? At this point, this is where we could do our little calculation to figure out which one's the limiting reagent. We're going to set each of these guys equal to 0, so we could do that. So this would be 6.200 minus 3X is equal to 0. We're basically going to bring the 3X to the other side and divide by 3. That would give us 6.2 divided by 3. gets us an X value of, we'll call it 2.067 moles. We're going to set the other guy equal to 0, which pretty much is the answer there. X would equal 0.2587 moles. In this particular case, we see that this guy here is the smallest number. That means that the N2 is the limiting reagent, and by default, the H2 is the excess reagent in this particular problem. Any questions on that? A reminder that once you do that, that is the X value that you want to use. So you might want to just kind of cross that out so you don't use it for anything. Once again, that X value is every single X value that we see in this table. Right? And again, that's what's going to allow us to kind of quickly calculate everything. So we'll do what the question asked, which was we would produce. So from the table, we can see that at the end, the moles of NH3 is equal to 2 times X, which would be 2.2587 moles of NH3. And that would get us 2 times 0.2587, 0.5174 moles of NH3. And if we want the grams, we could use the molar mass now of NH3, which is 1401 plus 3 times 1, basically. It's about 1703. So using the molar mass from the periodic table, we see that we did produce here about 8.813 grams of NH3 in this case. This would be, once again, what is referred to as the theoretical yield in this case. First off, any questions on that? Now, it wasn't asked in this problem, but once again, we could very quickly figure out how much of the excess reagent was left over. And if we wanted to do that, we would go back to our table and see that this is our excess reagent. So if we wanted to do that, which is a very common question, we would take 6.2 minus 3 times the X, which was 0.2587. And that would give us about 5.4239 moles of the H2 left over, which if we times it by the molar mass of H2 would give us about 10.9 grams of it left over. And we started in this case 12.2 grams, 12.5 grams of it. So we only use about 1 point so much grams of it in this particular reaction. Any questions on how to do this here? So like I said, if you like this approach, you could use it. It's also good practice for 200B. You do ice tables in every calculation pretty much. So I'll help you out there as well. Any questions on where any numbers came from or anything? Okay, so I think what I have here, and I'll scroll through it, is sort of the alternative approach to the problem we did before. So again, here's an alternative approach in case you want to look at it later if you want to review it. But this way, what they're doing is figuring out if you wanted to use up one of the reagents, how much of the other one would you need to put in there, and do you have enough? So the first step is pretty similar to what we did. It would go through, and basically this calculation is if I want to use up all of the aluminum in this reaction, I would need to put in there 367 grams of the iron 3 oxide. And the amount of iron 3 oxide we started with is 601. So we definitely have enough of it. So that tells us that that is the excess reagent. And by default, the aluminum here would be the limiting, just like we found as well. So this is a very common sort of approach as well. Once you would do that, you then would use obviously the limiting reagent, which is the aluminum, and figure out how much product that you would produce. just like we did sort of through the table, and they hopefully get this, whoops, the same amount as we got, obviously 234 grams. And in this case, as you can see, if you want to figure out how much of the other one, you have to go back and start another calculation, or how much of the excess you would have to go back and start another calculation. So it is a very common approach. And again, like I said, the third common approach is just to simply do two separate problems, and whichever one gives you the smallest amount is your limiting reagent. Any questions on any of that there? Like I said, I don't care which one you use, as long as you use a legitimate approach. So let's talk a little bit about yield. So we touched a little bit upon it here by these calculations. There are three different types of yields that we're interested in. One is the theoretical yield, which is really what we've been calculating. Theoretical yield is the maximum amount of yield that you should produce in a reaction based on your starting amount of reactants. So it is basically, if everything went perfect, you weren't a klutz and spilled anything on the ground, there was no side reactions or anything like that. If everything went 100% perfect, that is the maximum amount of product that you should produce. We know in reality, things do not go 100% good all the time. You know, things stick and flash. You don't get all the stuff out. There's maybe some side reactions that occur. So what we actually see is what is referred to as the actual yield. And the actual yield is pretty much what the name implies. Is actually how much you get when you physically go and do the experiment or the reaction. The good news about the actual yield is, in textbook problems, they typically give it to you. So they'll somewhere along there say, hey, you produce this much of this product or something like that. So the actual yield is usually given to you. The theoretical yield you do need to calculate, and usually it will be either a basic stoichiometry problem like we did, or it will obviously be a limiting reagent type problem, but you would have to calculate the theoretical yield. Putting both of those together give us a popular yield, which is known as the percent yield. The percent yield is the actual yield divided by the theoretical times 100, and it tells you, you know, how good the reaction went. Closer to 100 here is what you're shooting for. You know, if you got a percent yield of 20, you did a pretty crappy job. You've lost a lot of stuff along the way. You know, if you got in the 90s, that's really good and stuff like that. Can you have over 100% yield? The answer is yes, and it also means that you probably also screwed up somewhere along the way. A very common way that people get, you know, maybe over 100% yield is in experiments, kind of similar to what we did. For example, maybe we did a reaction and you made a precipitate and you filtered it in, like, say, your filter paper or something like that. And you were not patient enough and let everything completely dry, and you reweighed your filter paper and it still had water weight, which you are now counting as the weight of your product, which obviously was not really your product, it was just water weight. So usually if you get over 100% yield, it's not so good. Usually something is wrong like that. So it's a very common thing, kind of similar to what we did. You know, if you didn't hit constant mass, you maybe still had some water weight in there in your product, when we kept, you know, kind of weighing and cooling and weighing and cooling. So let us try one here. Why don't you try one here and see how you do. We take 2.46 times 10 to the 7 grams of TiCl4. The molar mass is given to you, so that's what you would get from the periodic table right there. That'd be grams per mole. And magnesium, which is also grams per mole there. Calculate the theoretical yield of titanium there, and calculate the percent yield if you made 5.42 times 10 to the 6 grams of it. So take a few minutes, see what you come up with. Here, so we got some big numbers, but really works the same way. Once again, looking at this, we have grams of the TiCl4, which is a reactant. We also have grams of the magnesium, which is a reactant. So once again, that tells us that this is a limiting reagent type problem, as we do have enough information to get us into moles of each of those. So we'll start like normal here. We're going to have our balanced equation, which we do. In this case, we're going to convert to moles. So starting with our 2.46 times 10 to the 7 grams of TiCl4. Once again, you would get that number that they gave you from the periodic table if you needed to look it up, the molar mass. And that is 189.7 grams per mole of TiCl4. And that gives us 2.46. Make sure you use your exponent button. 7 divided by 189.7. We'll call it 1.30 times 10 to the 5th. and this would be moles of TiCl4. We'll do the same thing for our other guy there, which is magnesium. 1.13 times 10 to the 7 grams of magnesium. Once again, that number comes from the periodic table, the 2431 grams per mole. The molar mass, 1.13 exponent 7 divided by 24.31. 4.65, it looks like, times 10 to the 5th moles of magnesium. So once again, pretty much working the same way as before. We have our moles. I'm going to do the table here. So let me get that set up here. So we had here, let's see here, TiCl4 plus a couple of magnesiums and Ti plus 2 MgCl2. All right, so initially we're going to use the moles we just calculated. So that is 1.3 times 10 to the 5th moles and 4.65 times 10 to the 5th moles for this guy. Once again, we're going to assume 0 for our starting amounts of our products. Assuming that this reaction goes from left to right, we're going to do our change, which is important because it also is our stoichiometry part. So this would be minus x. This would be minus 2x, once again, for the 2 that is there. This would be positive on the other side, x, and this would be positive 2x there, once again, for the coefficient that we see there. Obviously, the other ones are 1s, so that's why I don't put anything. Carrying it down here, we end up with 1.30 times 10 to the 5th minus x, 4.65 times 10 to the 5th minus 2x, x for this guy, and 2x for that guy. Any questions on the table setup here? So at this point, we're going to figure out our limiting reagent. So setting the first guy equal to 0 makes it pretty easy to figure out this guy. It is going to be the same number. So x here would be 1.3 times 10 to the 5th moles. Setting our second guy equal to 0. That means basically we're dividing by 2 here. That gets us 4.65 to the 5th divided by 2. Gets us a 2.33 times 10 to the 5 moles. At this point, it is the one that is the smaller number that's going to be our limiting reagent. So in this case, the smaller number is this guy right here, right? That's a smaller number, which means we don't need this anymore. That also tells us that this is the limiting reagent. And the magnesium here is the excess reagent at this point. Any questions on that part of it there? And as we've been talking about, once we have that X value, once again, that X value right there is every single X value in this table. And in this particular case, we are interested in TI, I believe. So we are interested in this guy right here. So that means that from the table, the moles of Ti is equal to X, which means it is 1.3 times 10 to the 5th moles of Ti, which we could use the periodic table to get our grams, which would be 4788 grams per mole. That is the molar mass from the periodic table. And that would get us call it 6.22 times 10 to the 8 grams of Ti. This would be our theoretical yield, right? Any questions up to there? Now, we won't do it in this problem, but again, if you wanted to also figure out how much magnesium chloride, you would just take 2 times your X value, right? And that would get you the moles of magnesium chloride. You could also then multiply by the molar mass to get the grams that you would produce of that. And like we did previously, you could also go into the magnesium line at the end and figure out how many grams or moles of magnesium is left over by doing that. But in this case, we'll just do what it asks, which is actually the percent yield. So now we calculated theoretical yield. The actual yield was given to us there in the problem, and it was there before I scribbled on it. Looks like the actual yield, 5.42 times 10 to the 6 grams. So once again, the actual yield is typically given to you in the problem. We just calculated a theoretical. That is going to allow us to calculate the percent yield. I think I wrote 8, but that should be 6. Sorry about that. That should be 6 there. Looks like an 8, but it should be a 6. So again, our theoretical yield 6.22 times 10 to the 6, not 8. I'm sorry about that. There we go. So now our percent yield would be our actual divided by our theoretical times 100%. Actual was 5.42 times 10 to the 6 grams divided by our theoretical 6.22 times 10 to the 6 grams times 100%. And we end up with looks like 87.08%, something like that, or 87.1%. Not too bad of a yield, not the greatest, but it's at least high 80s, so that's pretty good. Any questions on any of those steps there? Any questions on limiting reagent problems, anything like that? All right, so I'm going to scroll this across in case you want to look at it. This is the one we just did again with an alternative approach, doing the which reagent do you have enough of? So that is converting our guys into moles like we did before, in case you want to look at it. This is the calculation to figure out, once again, if I want to use up all my moles of TiCl4, how much magnesium I need to put in there. And once again, at this point, we would compare it to our starting amounts of magnesium, which is above, and see if we have enough. And as we saw here, we do have enough. And that means that the TiCl4 was the limiting. We would then use our limiting reagent and do our stoichiometry calculation to get our theoretical yield and then into our percent yield at this point. Any questions on any of that there? Okay, so we will lay it up there for now here.